All right, so I'm now going to prove proof 2.1, which is that we want to show that, so there's a couple of things we're going to prove on this. We're first going to show Bessel's inequality. So this is Bessel's inequality here. Then we're going to show that if we define this sequence as basically being equal to the projection of x onto EI, which is an element of an orthonormal sequence, times EI if you take the infinite sum of those, or sorry, I'm not even taking the infinite sum, I'm just taking the sum up to the nth position. I'm going to define that partial sum as S sub n. And what we want to do with this is that we want to show that if we take the limit, we get a convergent, it converges to something we're going to call x hat, and that this x hat is also a member of our subset M, or sorry, not our subset M, but rather our closed subspace M. Which I don't have mentioned here, but you should keep in mind that we are dealing with all of the things I'm talking about here. All of these are in a subspace, a closed subspace called big M. All right, so first of all, we want to show Bessel's inequality. So the way we do that is we first note that if we have, if we take the inner product of x and S sub n, the partial sum, and if we do this where we add and subtract S sub n, we end up with the following. Now x minus f sub n, the inner product with S sub n is going to be equal to 0 because x minus S sub n is missing the first nth entries. Those all become 0. And so we basically have the zeros up until the nth position after n plus 1, or n plus 1 and afterwards it's back to being the regular x. But this is actually 0, and then S sub n, the inner product with itself, just becomes the square norm of f sub n, S sub n I should say. Next we want to show that S sub n squared is less than or equal to x sub n, the norm squared, and we do that by taking x minus S sub n, and we basically just write that out, do the algebra, and we're left here with this term, which we just showed is equal to S sub n, the norm squared. And so again, we do the algebra, and we find that because we are dealing with a norm, it has to be greater than or equal to 0, and we can rearrange and we end up getting the result we wanted. Now I will note here that if we write out this, S sub n, the inner product with itself, if we write that out, what we find is that we get a bunch of inner products. So we, some of those inner products basically simplify down to the xi sub I. And then the cross products, if we have any terms that have like an E sub I and an E sub j, where I and j are different, those are going to be equal to 0 because we are dealing with an orthonormal basis. So we can rewrite S sub n as just being equal to the square of the inner product of x with E sub I, and this is actually just equal to xi I, the elements of our vector x. And we have that for any finite sum, this has to be less than or equal to the norm of x squared. Now I will point out that this is a non-decreasing sum, and we know from real analysis that if we have a non-decreasing sequence that's bounded above, the limit must be as well, and so we can take the limit on the left hand side and we get Bessel's inequality. Now we want to show that given Bessel's inequality that this sequence here converges, and it does, because if we write this out, we know that its square norm converges. So if the square norm converges, then so does the norm itself. And then we also have that we're going to label this sequence as being x hat. And we know that this x hat, it has to be an element of M because, as I mentioned, M is closed. So if we're dealing with a convergent sequence in a closed subset, then its limit point has to be in the closed set as well. And the final point we want to show is orthogonality. So I want to just start off with the finite n case. So x minus n, take that, make it orthogonal, or sorry, take the inner product with any of our orthogonal bases, E sub j. And we can use the linearity property of the inner product, we get that. And if n is greater than j, what we end up getting is xi I minus, this should be xi j minus xi j is equal to 0. And so we can just basically take advantage of the continuity of the inner product. So x minus x hat is equal to x minus the limit as n goes to infinity of S sub n with E sub j. And we can pull out the limit, so we end up getting x minus S sub n, the inner product of that. And we know that the limit of this, since our j is fixed, is going to be equal to 0, because eventually our n will be large enough that we are picking up this xi j, and so that's equal to 0. And so we can conclude that x minus x hat is an element of the orthogonal complement of our subspace M.